So there are different kinds of chemical equations. A molecular equation is what we think of as a regular chemical equation. And this shows neutral formulas for each compound. And here we're talking about aqueous reactions. It'll show the formulas like they were molecules, but they're ionic compounds, so they're not molecules. So potassium hydroxide is written together. That's the formula for the compound that was dissolved in the water. And magnesium nitrate is written together, even though this is aqueous. In actual solutions, those ions are separated. So a complete ionic equation is going to show all of the species, and here species just means a particular substance, like an ion or a molecule or a compound, all of the species as they're actually present. So potassium hydroxide, aqueous, is actually present as potassium ions and hydroxide ions separate from each other. And so in the complete ionic equation, we're going to show that. And we'll get to examples on the next slide. The net ionic equation shows only the species that actually are involved in the chemical reaction, only the things that change. So writing complete ionic equations. You start out with your regular molecular equation, and then if you have aqueous strong electrolytes, you're going to show those as ions.
Sorry, is it okay if we go back to the last page really quick?
Mm-hmm.
I just want to make sure I understand. So in molecular, those equations, even though they might not actually, like the aqueous solution is, like the KNO3 is not going to be, they're not going to be together really.
Right.
But we're just showing them.
Right.
Okay.
So the molecular equation, we show the potassium and the nitrate as being together, even though we know that in an aqueous solution, the potassium ions and the nitrate ions are floating around completely separate from each other. Yeah.
And then you're going to talk about it.
Yeah.
Okay.
So if we have strong electrolytes, remember a strong electrolyte is something that separates into ions completely. So these are going to be soluble salts, soluble ionic compounds. They separate into ions. We're going to show those as ions instead of as a neutral compound. And also strong acids and strong bases. Now, strong bases you don't have to worry about because all of the strong bases are also soluble salts. Things like lithium hydroxide is a strong base. But lithium hydroxide you would show as an ion anyway because it's a soluble ionic compound. So the strong acids we do have to consider, and they are HCl, HiHBr, nitric, sulfuric, and perchloric. Those are the strong acids. Those show up a couple slides later, but we need to know which ones they are right now. Remember, what makes an acid strong is that it separates into ions completely. There are only 6 that do that. So what we need to do is we need to remember the 6, and if we see an acid and it's not one of the 6, then we know it's a weak acid. So soluble ionic compounds in strong acids we're going to show as ions. If we have something that's insoluble, meaning its state is solid, we're going to leave that and show it as a molecule. If we have something that's a weak electrolyte, that would include a weak acid, we're going to show it as a molecule. Now, weak acids do form ions, but they only do it a little bit. And so we're showing what it mostly is. It's mostly the intact molecule. So those things are going to be written as molecules and then non-electrolytes, things that don't form ions at all. So if you look at the state and you see solid, liquid, or gas, you do not separate it into ions. The only things that get separated have AQ. Okay. Almost everything that's AQ gets separated. The exception is weak acids. So you can do pretty well if you just separate everything that's aqueous. You'll get some wrong, but you'll get most of them correct. But if you want to really do it right, the weak acids don't get separated.
Professor?
Yeah.
And they're weak because they're weak conductors.
They're weak conductors of electricity because they only form a few ions. They form a few ions, and so electric current can flow, but they don't form a lot of ions like a strong acid. Yeah. So here we have our lead and potassium example again. So here is the molecular equation. So to write the complete ionic equation, I'm going to look at this lead nitrate aqueous. This is an aqueous substance. This is not an acid, so I'm going to separate these into ions. So I have one lead ion. That lead ion has a charge. When we write the ions separately, we have to write their charges. So this is Pb2+, it's aqueous. And then in 1 unit of this, I have 2 nitrate ions. So then down here, I have 2 nitrate ions with their charges, and those are aqueous. So this equation's balanced, and if I do my complete ionic equation carefully, it will also be balanced and I won't have to mess with it. KCl, aqueous, soluble ionic compound. So in the equation, I have 2 of those, so then I have 2 potassium ions and 2 chloride ions. Over here, I've got a solid. If it's S, L, or G, just copy it down, don't change it at all, because that's a precipitate. It's stuck on the bottom, it's not separate. And so we're showing it as it actually is. And then here we have another aqueous substance, and so 2 moles of that gives me 2 moles of potassium ions and 2 moles of nitrate ions. Any questions? So you could sort of think of this as relationship status, right? When lead and nitrate came to the party, they were not in a relationship. And when potassium and chloride came, they were not in a relationship. And after a little bit of time at the party, now lead and chloride are in a relationship, but potassium and nitrate are not. Question? Okay, that's okay. Anybody have any questions? So here is that complete ionic equation again. It's kind of spread out. So at this party, lead and chloride got into a relationship. What happened to nitrate? Maybe got a little buzzed, ate too many chips, but nothing life-changing, right? So here's nitrate ion, and here's nitrate ion as a product, and it's not changed, right? There's potassium ion to start with, 2 potassium ions, and here we got 2 potassium ions. They didn't change. We call those spectator ions, because they're just watching the action. So it's not really nice to think of them watching those people making out, but maybe a boxing match, right? Go to a boxing match, and you got 2 guys beating each other up in the ring. Personally, I don't understand why that's fun to watch, but whatever. So you got the 2 guys beating each other up, and then you've got all these people in the stands spectating, right? They're watching. And so in the newspaper, does the article talk about what the spectators were doing or what they were wearing or what they ate for breakfast or anything? No, it talks about the action in the ring, the guys that were doing something. So lead and chloride is where the action is. And potassium and nitrate are the spectators. So the net ionic equation, we cross out the spectator ions because they're just watching, they didn't participate. And we just write what actually happened in the chemical reaction. It's a little bit like your gross paycheck versus your net paycheck, right? Your gross paycheck is much bigger, and the net paycheck is smaller because they take out taxes and this and that and the other thing, right? But this is the bottom line. The net paycheck is what you actually get to put in the bank and do stuff with, right? So that's the important thing. So when we cross off the spectators, what we have left, we just copy down, and that's the net ionic equation. Any questions? This is a little bit like mathematical equations, where if you had A plus B is equal to A plus C, you say, well, I can subtract A from both sides, and I've just got this simplified B equals C, right? Same idea. Yeah. How do we know which ones are the spectators? That's a good question. We're looking for something that is present as a reactant and a product exactly the same, not changed. So here we have lead, and here we have lead, but now lead is part of this compound. 2NO3, 2NO3, exactly the same. We just cross them off. Any other questions? Yep.
So to find out the net ionic equation, do we have to be given the full formula, or will there be, like, an example, like, will we have to predict the formula and then find the net ionic?
Yeah, so what are we going to be given and then expect to produce this net ionic equation? You could be given the two reactants, and you have to predict the products, identify which one is soluble, which one's insoluble, and then come up with the net ionic equation. It is possible to write a net ionic equation without doing a complete ionic equation, but I don't recommend that when you're first starting out. It's best to write the complete ionic and cross out the spectators. Yeah.
And this might be a problem with more complicated equations. Are we going to come across something where there are more than one possible solution, and we just kind of have to make an educated guess? I don't know.
That's a good question. Are there going to be situations where there's more than one possible right answer or more than one possible apparent answer? The only place that happens in the class is occasionally they'll give you a transition element like this, and they won't really specify what the charge on it is as the product. And that actually doesn't happen in these sorts of precipitation reactions. It happens in a different kind of reaction. That's about the only iffy thing. And I definitely won't try to trick you with something like that on an exam. So let's do an example. So here we're given the balanced equation and asked to write the complete ionic and net ionic equations for this reaction. So anything that has AQ is a possibility for getting split into ions. So we see AQ, then we ask ourselves, is it an acid? This is an acid. Is it a strong acid? Yes. So I'm going to separate that into ions. Remember, in Chem 1A, ionic things always have just two ions, one cation and one anion. We're not going to have a ménage à trois or anything like that, right? Just two people. So here we've got hydrogen ion and iodide ion. Those are the two ions that form from HI. There are two of these, and so I'm going to get two hydrogens and two iodides. So you could imagine making this with the model kit, and you've got, forget what color iodide is, purple. You've got a white ball and a purple ball, and you have two of those units, and you take them apart, you're going to have two white balls and two purple balls, right? That's all we're doing here. And then this one says AQ. Is this an acid? Nope. Okay, we don't have to worry about it. We're going to separate it into ions. Two ions, barium and hydroxide. So barium ion and hydroxide ion. Now, it's not OH2. That's a polyatomic ion. It's hydroxide. The parentheses tell me that there's two of what's inside. So I have two hydroxides. I'm not going to write that as O2H2, 2 minus, or anything funky like that. Any questions so far? And then I've got my arrow. Next up is H2O, and the state is liquid. So what do I do with it? Just copy it down. 2H2O liquid. Go on to the next one. The next one's also aqueous. Is it an acid? Nope. Okay, split it into ions. So we got barium ion. And iodide ion. And there's two of the iodide ions. If you're iffy on your polyatomic ions, on predicting ion charges from the periodic table, you need to go back and work on that, because otherwise this is going to be super, super hard. So there's my net ionic equation. I'm sorry, my complete ionic. So we could call that complete ionic equation, CIE. I made that up. To find the net ionic, yeah.
Well, I'm just curious, why are you writing the charges? I just don't understand it. It's like for barium 2+, like we know it's 2+. Why are we writing it?
Okay, that's a good question. Why are we writing the charges? Because this is barium ion in solution, and if I wrote it without the charge, that's barium atom. And that would be a solid, and it wouldn't be soluble. Yeah. So up here, we don't show the charges when we write a formula for an ionic compound, because they're together and it's an ionic compound. When we separate them into ions, then we do have to show the charges. It's an excellent question. Anybody else? So to do the net ionic equation, we're going to look for which reactant is also present exactly the same as a product. So what's one of those? There's 2I- aqueous, and over here there's 2I- aqueous. So iodide, oops, crossed it out with the eraser. The iodide wasn't changed. What else didn't change? Barium. I have barium ion on this side, and I have barium ion on that side. So for my net ionic equation, and this is an abbreviation that people actually use, NIE, net ionic equation, I'm going to copy down everything I didn't cross off. 2H plus and 2OH minus, making 2H2O liquid. If I've tracked everything correctly, it'll be already balanced, but there's something a bit funny about this one. A balanced chemical equation should have the lowest ratio of whole number coefficients. Here I've got 2, 2, and 2. I could divide everything by 2, still have whole numbers and be balanced, right? So ideally we should do that and get rid of those 2's. That's a minor point. Any questions?